just to look at the syllabus for a second. I put this up here, but the link is broken, and I'm not sure why. I've looked at it from every angle, so I'll have to figure it out. So, apologize for not having sections 3 and 4. I did update sections 1 and 2 slightly, so you might want to download the new version. I'll fix this link today. We will get pretty far along. I don't know if we're quite finished chapter 13 today, but we'll get close. We may have to finish a little bit Monday. And then starting Monday, we're going to move into regression. And regression will take the rest of the semester. Whether or not I do anything in logistic regression, which is the last part, I'm not certain yet. That's a topic that I want to break out separately, but I may just give you an example of, depending on how far we get with regression, I may just break out an example of logistic regression because it is a very important topic, and I discovered that some of our students were not taking Stat 555 on categorical data analysis, and logistic regression is taught within that course. It may be taught in other places. I don't. It's possible that Phil Turk is teaching it in 645 to some degree. So at any rate, unfortunately that link does not work. The lecture from last time is posted, and I'll be posting. I usually can't get it done the day I do it because it takes a while to convert it to MPEG, and then I have to upload it. I get up home, it's very slow to upload it. So I don't always get it done until later in the night or even the next day. So what I want to do today is to go in and just briefly review what we did in 512 in the analysis covariance, and in particular in sections 1 and 2. And I think that there may be chapter 12. I need to be in chapter 13. So I'm going to look at section 1. Section 1 is actually 1 and 2 in one file. I'm going to clear the console here and set the directory to the file. So I'm going to go ahead and knit this. And then I'm going to blow this up a bit so you can see it better. So again, this is our basic model, mu plus alpha sub I plus beta times the regressor with the x variable. And we're assuming the alpha sub I you can think of as an index variable representing the different groups. And on the other hand, the x sub ij, in other words, it's an I and a j because it's the jth observation in the ith group for the independent variable or the regressor variable. The outcome variable y is ij. Again, that's the jth observation in the ith group. And then you have an error term, of course. Generally speaking, in this case, the alpha is fixed. This can be generalized in two different ways. One is, instead of having a single factor here represented by the alphas, you could have a factorial, for example. You could have alpha sub I plus beta sub j plus alpha beta ij. And then, of course, you would need to have another subscript for the x. You would have to have xijk, jk, where you have the kth observation in the ith level of A and the jth level of B. So I could generalize my treatments, having a single treatment. I could have multiple treatments. I could look at interactions. The other generalization is that you could have multiple regressors. That is, instead of just a single x, I could have multiple covariates. And that's a very common problem. The analysis of covariance can also be used in designed experiments, and in particular it can be used in hierarchical models. And the covariance, there you have multiple levels. You have a sort of a whole plot level and a subplot level. And the covariate could be associated with the whole plot or could be associated with the subplot. So there are lots and lots of generalizations for the ANCOVA model. We probably won't have time to do that. Again, once we get into multiple regression, if we have time, I could show you an example that generalizes covariance. If, of course, you remove the alpha and don't have any factors, then you're in what we call the regression setting. These are all linear models. Everything is in the book is a linear model, except for the logistic regression was what we call, it's one of the types of a generalized linear model. It's generalized because we've been assuming up till now that the error terms are normal. Suppose the error term is binomial. So you have a discrete random variable. And in a binomial case, you're looking at the number of successes in so many trials. Well, the binomial experiments are incredibly common in both ecological applications and also in the health sciences. So you might have, for example, you might have the 5-year survival rate. So a given patient either survives or doesn't survive for 5 years after, say, cancer surgery or heart surgery, whatever. So there are lots and lots of cases that we have outcome variables. The most common case is when they're binary. In other words, it's one or two classes, like you survive or you don't survive. But you can also have multinomials where the outcome variable could be one of a number of classes, more than two, or you could have an ordered outcome variable where it's in classes, and the classes are ordered from some smallest to largest class. But again, they're ordered, they're not on a numeric scale, they're on an ordinal scale. So you can have ordinal regression type models. Again, that's getting beyond this course. So clearly these calculations that are given here for a single y and a single x, they're complex in this case, and they're essentially impossible to do when you have multiple x's. If you have multiple covariance analysis, it would be very, very difficult, to try to do these by hand. That's why we're moving this course more towards computation and R-based course. So we talked about advertising and profit, and it was related to different types of media for advertising. And the question is the method you use for advertising, does it depend upon the number of employees in the company? So we did an analysis of covariance where we had the response variable is profit, and the categorical variable or the factor is median, and the employees is the covariate. And what I showed you initially, that you could write this in two different, using LM, that the order matters because what it gives you the result, or what are called type 1s, the squares, are sequential. So in the first one, it would fit median and nothing else in the model. In other words, it wouldn't adjust for employees. Whereas the second one, the second term in that model has employees. The employees adjust for median. And if I write it in, and you notice that I get a different answer depending on, it's the same model in a sense, but I write it in one I have median plus employees, the other one I have employees plus median. And since they're sequential, the order matters, and you get different sums of squares for your different terms in the model. I mentioned that you could use the car library with the ANCOVA, or ANOVA, function with a capital A, and that would give you what are called type 2 sum of squares, and that would adjust each term for any other term at the same level or lower. In this case, employees and nutrition are all first order, they're at the same level. If I had an interaction in the model, then it would look at the interaction adjusting the first level terms, but if the first level terms would not adjust for the interaction. So that's type 2. Type 3 would adjust everything for everything else in the model. So these are called type 1, 2, and 3 sums of squares. by default, R does type 1, and that creates certain problems. I talked about the model matrix, and the model matrix is the actual, this is the actual data that's used to estimate the coefficients. And you have an intercept, and that's for the mu term. You have the data for the employees, and that corresponds to the beta term. And then you have medium 1, which corresponds to alpha 1. You have medium 2, which corresponds to alpha 2. And then you have, of course, the minus 1, which is minus alpha 1, minus alpha 2, which is really the alpha 3 term, because we have a constraint. The constraint I used was that alpha 1 equals alpha 2. The sum of the alpha sub i's equals 0. Sorry. So if I use a summary statement, it actually breaks it out according to these 4 columns. It actually gets the estimates of the mu, beta, alpha 1, and alpha 2. And these are the estimates, so standard errors, and the test. Now, in this case, it's doing the test for employees is okay there. Okay, this actually does a t-test because it's doing single degree. Each of these has a single degree of freedom, so it's doing a t-test. So if you have a f-test with 1 degree of freedom, you may not know this, but an f-test with 1 degree of freedom in the numerator is equivalent to the corresponding t-test. So if I square the t, I get the f. So I believe this 17.46 squared corresponds to the f-test in the previous ANCOVA table, or ANOVA table. I showed you last time how you could draw the regression lines, and again, these are for the 3 different groups. In this case, we have 3 groups. The slope, this is the common slope model, so we're assuming that we have a common beta. The beta does not depend on the group. In other words, the regression does not depend on the group. So I went through last time how you construct this using these coefficients up here. So for example, 55.78 plus a minus 13.11 would be the intercept for the first group. And the 55.78 plus 1 would be the intercept for the third group, and then the 55.78 minus these two gives you the intercept for the third group. And so the graph looks like this, and I had plotted the original data using different symbols for 3 groups. Now, this particular experiment actually is a very good fit. There's not much variation about those regression lines. You can see that the circles, the triangles, and the pluses are very close to the 3 regression lines. Then I showed you how to do the sample means, which the sample means are just the simple means and not the model means or what we call the least squares means. And so we simply t-applied, we got the means mapped over the medium for employees and profit, and we plotted those. And those are those red circles. Because I said I want to plot these employee means and profit means using red. On the other hand, I used the model right here. I actually constructed a data frame for 1, 2, and 3, and then I used the mean in all cases, because I'm actually going to standardize. What I'm in effect doing is standardizing the means as if they all had the same age. The problem is the number of employees, not the same age, the number of employees. I'm standardizing them to the same number of mean employees, which is actually 31, I believe. So what I mean by standardize is I'm actually computing these means using the model. So here's the model, and here's my new. I'm going to get predictions for each of these 3 groups at the mean employee. And so in effect what that does, it says if I remove the employee effect, what are the means? Well, the means are going to be, we're going to standardize it at the at the grand mean of the employees. And so the blue, and there's actually a blue circle here, but the red overrode it, and then there's a blue up here. So these are actually what are called the model. These are the means, or what we call the adjusted means, the least squares means, the model means, all mean the same thing. We're adjusting for the effect of employees. In effect, this means slides up the regression up to here. This one is already here, and this one slides down the regression to here. That's the adjustment you get by having the covariate. And in this case, it's a fairly significant adjustment. So now here are the predicted values and the residuals. And so if you do diagnostics, one of the things you commonly do is plot the predicted values, which are the fitted values of profit, versus the residuals. And they should be pretty much centered about the 0. They're residuals, they're scattered about 0. And I'd like them to be scattered about 0 for all three groups, some above, some below. And that pretty much appears to be the case. So we reasonably meet the assumption, and then I can take the residual. You don't do these on the raw data. The assumptions are about the epsilon, right? The epsilon, those are the residuals. So we actually compute the estimated residuals, and we do diagnostics on those residuals, not the raw data, because the raw data have the group effect mixed in and the covariate effect mixed in. So you don't use the raw data. We use the residuals. Now notice that if I look at the residuals, they're reasonably normal. There seems to be a little bit of deviation on each end. Okay, so that's the gist of that section. Are there any questions? Yeah.
This graph is only the adjusted to the employees, right?
Yes.
So you only.
I mean, this is the raw data. Those black symbols are the raw data. I just use different symbols for the three groups. Okay? And then I fit a line to each group, but they have the same slope. Because we only have one beta. We're assuming that beta is the same for all three groups. So we fit three lines that are parallel to each other.
You say if you want to achieve F-test to the employees, you might need to adjust the median first, right? Because the section 1, first, the two models, you said you can also adjust the median first. So under what circumstances we need to adjust the effect of the median?
Okay. You want to adjust the median effect for employees, and you also want to adjust for employees for the median effect. So you want to adjust each term for the other term in the model. Now, when we talk about models of different levels, so we have, let's suppose we have A plus B plus A colon B. We have a two-way factorial experiment. Generally speaking, what you're going to do there is you're going to look at A colon B first and decide whether or not you need the interaction in your term. When you do that, you should be adjusting A colon B for both A and B. You want to look at the interaction effect over and above the main effects, which are A and B. Okay? And so then you make a decision. There's some issue about should you adjust A and B for the interaction. There's some issue about that. Type 2 would not. Type 3 does. Type 1 just, if you have A plus B plus A colon B, type 1 would fit A and nothing else. Then it would add B to the model, so you'd have A plus B, and not the interaction. And then it would look at the B effect adjusting for A. And then if you have plus A colon B, that would now add one more term to the model, A colon B, and it would adjust for both of the B and A, and that's sequential. But they're added one, and you can think of them as, you saw that with an A, then A plus B, then A plus B plus A colon B. In that order, it fits it sequentially, and it only adjusts what's before it in the model. Type 2, if you have A plus B plus A colon B, it adjusts A for B and adjusts B for A, but it doesn't adjust either of those for A colon B. But A colon B is adjusted for both A and B, because the way that type 2 works, given the order of a model, let's say a first order or a second order model. First order would be like A, second order would be like A colon B. It adjusts for that, anything else that's of the same order or lower. So a two-way interaction gets adjusted for any other two-way interaction and the single terms in the model, but it doesn't get adjusted for a three-way interaction, for example. And but a type 3 adjusts everything for everything. So it would adjust A, if you have A plus B plus A colon B, type 3 would adjust A for B and A colon B, and so forth. Now, which is the best? Well, there's some controversy about that. You could argue that you definitely, if you put an interaction in, you should adjust for the main effects and look at the additional contribution due to that interaction term over and above the additive terms in the model, which are the main effects. But do you adjust for the interaction given that you have the main effects in the model? That's where the controversy comes in. Some people would say no. Let me do another example. Suppose you have a model that's a polynomial regression. So you have an x term in the model, which is numeric, and you have x squared in the model, which is also numeric, and you have x cubed in the model, which is numeric. Then you would look at the linear effect, which is x. Then you could look at the quadratic effect over and above the linear effect, which is adjusting x squared for x. And then you would look at the cubic effect, adjusting for x squared and x. So the question might be, suppose you tested each of these, and it turns out that x is not significant, but x squared and x cubed are. Should you delete x from the model? The answer is absolutely not, even if it's not significant. And so, because if you do, it forces that polynomial through 0. In other words, there are certain things you really don't want to do. So there are reasons why you leave in lower order terms. Likewise, if you have A plus B plus A colon B, it's okay to drop out A colon B. But should you drop out A, suppose A is not significant, B is significant, and A colon B is significant. Would you drop out A? No. For the same type of logic. Because as an interaction, we need to adjust for the main effects, even if one of those main effects is not significant. It's a little bit tricky to think about, but if you think about it logically, you can get very bad results by dropping out lower order terms when the corresponding interactions are in. And that's part of the reason that we have these different types of sums of squares. The type 2 sort of adjust at the same level or below, and that's a logical thing to do. By default, R does type 1. You have to use that n of a function, which can give you type 2 and type 3. I think by default, jump uses type 3. I don't know if I answered your question, but it's a little more subtle than you might think at first glance. And I haven't seen a lot of very good discussions about this, including in this book. There are books that are more advanced that have a good discussion. Books, for example, that could be used in Stats 645. So one of the things that you just might keep in mind is that I think in this particular model, we have no interaction. You don't gain much by having different slopes. And you'll see that coming up here just a little bit later. When I go to the next sections, we look at that hypothesis of equality of slopes. And if we accept the null hypothesis that the slopes are the same, then we don't need the interaction between the covariate and the. Okay? So we'll get to that. So you'll see a little bit more of that. So what I'd like to do now is to go into section 3, and this actually has section 3. Oh, I think I'm still in. It's all in chapter, yeah. So what I'm going to do is to knit this, and we'll look at what we're going to do in the remaining sections of this chapter. Okay. Now this is the same example that we'll be looking at. So some of the assumptions of the model, and I'm talking about, there are assumptions about the epsilon too, like normality. And we also had an assumption that said the variances are equal. It doesn't matter which group they're in. It's all the same variances. It doesn't depend on, in other words, the variances did not depend on I, the group. And we also said that slopes don't depend on I, the group. So we want to look at those two assumptions. And then finally what we want to do is we want to say, well, is the covariate worth it at all? Is it worthwhile putting the covariate in the model? Now, it certainly appears so because those three lines, they decline steeply with each of the groups. And the adjustments to the means seem pretty substantial. So it seems like that we do need a covariate, but do we need to have different slopes? So we'll take a look at those kind of questions. Well, the book goes into details about, for the ith group, you can compute various sums of squares for the x's, the cross products x of y, and the sum of y squared. So again, if you were doing this by hand, these t's are just totals. So in other words, t squared sub I dot of x would take all the x's in the ith group and add them up and then square them. The t I sub dot for y would take all the observations in group I of y and add them up and so forth. And here we're assuming that the n sub i's are not necessarily equal. And so you could go through these calculations by hand if you want to. And by looking at, if you look at the sum of cross products, this term divided by the one for x, that actually gives you the regression coefficient. If you look at this formula, when you take an intro stat course, like Stat 211 as an undergraduate, they usually show you computing the slope in a formula somewhat similar to that. There are various forms of that formula, but they're equivalent to this. So if I take the sum of squares of the cross products, and divide it by the sum of squares of the x's, that actually gives me the slope for the ith group. Now, in those intro courses, you're not doing this. You only have one group. You're not doing regressions within multiple groups. Once you get the b sub I, that's the slope for the ith group, you can get a sub I, which is the intercept, by taking the mean of the y's in the ith group minus b sub I times x bar sub I. So this sort of implies right here that we're assuming that the slopes may be different from group to group. Now the variability about the regression line is simply the y sub ij are the observed data, and y hat sub ij are the predicted values. Now remember, in that preceding, in section 2, I got the predicted values. You may not remember that, and did I close it up? Unfortunately, I did. That was unfortunate. So if I go into, again, here, and I look near the bottom, someplace, yeah, here was the media fit. Media fit are like the y hats. That's getting the predicted values from the model. Well, now that's actually the model. That's not quite where I want to be. I need to be down a little further. Sorry. Here it is. It's profit fit. Profit fit is where I get the predicted. I'm using the function predict. And if I use the argument, I only use the argument media fit. So I have predict, and then the argument is the model. I get the predicted values. And then the residuals, what I call profit residuals, is simply profit minus the profit fit. So in other words, in this context, these are the y hats, that I get from the predict function. These are the y's, the actual data you collect. And if I subtract off the y hats, y minus y hats, I get the residuals. So that's what I did. And then I plotted the fitted values versus the residuals. In other words, xy, where x would be on the x-axis and y would be on the y-axis. So I have the fitted values on the x-axis and I have residuals on the y-axis. This is where I actually use different characters right here. And I drew a horizontal line there. Okay. So this is this is y, and the residuals are y minus y hat. Now the residuals, let me look at this just one more time. So I'm going to go down to the bottom to this plot. Now just take one of the particular sets. Take the circles. If I look at the distance of a circle from the horizontal line vertically measured, those are the residuals. So the residual for this particular observation from here down to here is a residual for that observation. That's a residual for the next. And another one is, here's one that's negative. Y minus y hat is negative, and so forth. And here's another one that's negative. So I had 3 positives and 2 negatives. And if I square those up and add them up, and standardize it by some n, it's actually n minus 2, I'm getting an estimate of the variability about the line fit with the circles. In other words, if the circles, I forget which group the circles represent. If this is group 1, if this is median 1, then if I take those vertical distances and square them and add them up and divide by n sub I minus 2, then that would be that'd be a sum of squares of deviations. That would be like a variance around that first line. In other words, s sub 1 squared for the first group. And if I do the same thing for the other 2 groups, I get an s sub 2 squared and s 3 squared, so forth. So the question is, are they the same? So if you look at this other, and I need to run this again. Someplace. Yeah. Oh, wait a minute. I'm in. Which one did I run? Did I run the wrong one? Yeah, I thought I ran that one. That should be 13.3. Yeah, it's right here. So in other words, for the ith group, these are the y's minus the y hat. Those are the residuals squared summed up over n sub I minus 2. So for s1 squared, that would take the circles, let's say, minus those vertical distances squared, because the y minus y hats are the actual residuals, right? I square them and add them up, and that's for all the circles. And then I divide n sub I minus 2. You want to guess why it's n sub I minus 2 rather than n sub I minus 1? If you were in step 211 and you computed the variance, you would have the sum of the y sub I minus y bar squared over n minus 1, right? Not n, but n minus 1. And the reason you have a minus 1 is because you had to estimate one parameter. You estimated mu. So you have y sub I minus y bar. Y bar estimates mu. You lose 1 degree of freedom, so it's n minus 1. But look at y hat. I have y sub ij minus y hat sub ij. I claim I lose 2 degrees of freedom because I estimate 2 parameters. What are those 2 parameters? Yeah, you have the intercept and slope. And you have that for each group. And so you have n sub I minus 2. So I get an s sub I squared, and I do that for each of the groups. And now I'm going to, so now I have 3 estimates of the variance, and I ask myself, are they significantly different? Well, we could use Bartlett's test. Here I use the Fmax test. And if I look at the 0.05 upper, if I look in the upper tail for 0.05, and there are A equals 3 groups, and N is 5, and 5 minus 2 is 3. So in the table, you look at 3 and 3, and you find out that the critical value would be actually 78.8. That's in the table in the back of the book. I probably should use Hartley's test. I mean, not the Hartley Fmax. I probably should Bartlett's test, would be better. And that's built into R, whereas the Fmax, I don't think it's built directly into R. Now, so how might you get these variances? These are actually the variances assuming you have different slopes. Okay? So actually what I told you last time, those variances in that table where I had the diagnostic plot, where I had the fitted values versus the residuals, those were actually the deviations or the residuals from fitting a common slope. That's not actually what we're doing. We're doing something similar to that here. And I could do that same plot. I didn't do it here. But I actually want the residuals when I fit different slopes. So the question is, if you look at the design matrix that you had a 1 for the intercept, you had the covariate column, and then you had columns for the alpha 1 and alpha 2. That's what we had in the previous model. So we had 4 parameters we could estimate: mu, beta hat, beta hat, alpha hat 1, alpha hat 2, and you could get alpha hat 3 is equal to minus alpha hat 1 minus alpha hat 2. So that's how we estimated before. Assumes a common slope. But here, you see, what I'm doing is I'm computing individual b sub i's, and then I'm using those in the fitted values here. So in other words, I'm actually assuming here that I have different beta sub i's. So how do I fit a model that I have different slopes in my covariate model? Well, there are 2 ways you can do it, but if you actually want the coefficients, there's 2 different models you can look at. One of the models lets you get the coefficients. The other model lets you test the coefficients are equal. So those are 2 different things. So look at the model. I have profit tilde median plus median slash employees. So what does slash mean? Slash means nested. In other words, the employees are nested within median. They're not crossed. Employees work for a certain company, and different companies have different advertising. So in other words, an employee is unique to an employee doesn't belong to multiple companies and therefore get multiple advertising mediums. One company has one medium. Now I have 5 companies with median 1, 5 companies with median 2, 5 companies with median 3. But any given employee is in a certain company, which means they're associated with just one medium. It's not crossed. So the way you represent nesting, so we talked about in 12.1, right? We talked about nested models. So the way we represent nesting is slash. So I have median plus median slash employees. So I'm looking at a model that has a main effective median. Of course, by default we always have the intercept. And then plus median slash employees. So you might ask, did I do the design matrix up here? Yeah, here's the design matrix for this model. So I have the intercept plus median. So the median has 2 levels. It has alpha 1 and alpha 2, and again, the minus 1s is where you get the alpha 3. So these first 5 observations are associated with the first group. The next 5 observations are associated with the second group, and the last 5 observations are associated with the third group. Okay? There are 15 observations there. If I look at y, the outcome variable, it's a vector of length 15. The first 5 correspond to those first 5 there, and the second 5, third 5. But look at the covariates. Remember previously the covariates were in one single column? Now I have the covariates split. I have median colon employees, so I have, here are the covariates associated with the first group, here with the second group, and here with the third. So in other words, I've broken them out with 3 columns instead of 1. So I'm actually going to be fitting and estimating the parameter associated with each of those columns. So, and they're going to be associated with beta hat 1, beta hat 2, and beta hat 3. So that's the underlying structure. And that's a matrix. In this case, we're trying to estimate, instead of, previously we were estimating 4 parameters, now we are estimating 6 parameters. So we have a little more complex model. I mean, of course it's more complex because you are, you're trying to estimate different slopes within each group, whereas previously we had a common slope. So I fit this model, and I'm going to call the predicted value, the profit fit 2 is the model. It's the model for this, multiple slope model, where we have different slopes for each group. So profit fit 2 is the model that we have for it, and I'm not sure that's the best notation. I guess it works. I'm not sure this is the best notation. What did I call it before? Yeah. Oh, this is what I want. I called it media fit. I should have called it media fit 2, because profit fit was what I was using for the Y hats. I should have called this media fit 2. I'm going to change that before I post it. That would be more consistent with what I did in the first couple. So what I call the profit fit 2, that's actually the model object. And now, in order to get the residuals, the profit residuals 2, now that is consistent. I take profit minus the predicted value of profit fit 2, which should be median fit 2. So those are the residuals. And then what I can do, those are the residuals for the whole model. And then what I can do, you might say, I'm using something, you might ask, why don't I just do, if I want the variances for each of the group, for each of the median, what you would say, well, why don't you just use t-apply, and then you have profit residuals 2. Suppose I said t-apply, and the first argument would be profit residuals 2, comma, median, comma, var for variance. And that would create a variance for each of the residuals for each of the 3 medians. You would say, why don't you do that? That's really what we need, right? So if you look at, I don't know if I ran it. So if you look at the outcome, you'd say, well, isn't that what I want right here? The problem is, if I did that, it would divide by n sub I minus 1. And I want n sub I minus 2. So what I had to do is write my own function. Because I would have gotten something close, but you would not have reproduced the answers in the book. Because I would have divided by n sub I minus. If I would just say t-apply, profit residual 2, comma, median, comma, var, it would get the variance for each group for the residuals, which is almost right, except you're dividing by n sub I minus 1. So what I did is I wrote a function which takes the residuals and squares them and adds them up. So I'm getting the sum of squares of the, so if you look at this formula up here, I'm getting the sum of squares of the residuals, and then divided by n rows of x minus 2. Now x, this function gets applied to each median. So x will be a variable that corresponds to a vector for the first group, then the second group, and the third group. And the number of observations is always 5, so the number of rows of x will always be 5 minus 2. And so I wrote a function, and the only difference between this function and the variance is this 2 right here. If I had a 1 there, I wouldn't write the function if that was okay. So I wrote a little function, and I said by data frame. So I'm doing this within the context of a data frame, and then I coerce it to a vector, and then here are the actual 3 variances that are computed. Okay, those are the same as in the book. So now I could use Bartlett's test on that, or I could do the Fmax test. I did the Fmax test, which looks at the max variance divided by the min variance. So this residual variance 2, these are the variances. I'm looking at the max over the min, and it's a 1.845. The critical value with degrees of freedom 3 and 3 is 27.8. I'm not even close. Not even close to being significant. So I fail to reject null hypothesis. And in this case, there's very strong evidence that the variances are pretty similar. Now you may say, well, they do differ. Yeah, they do. 7.0, 6.1, 3.8. I mean, this third one seems like it's a bit low in particular. But again, when you sample variances, even if they're the same, the variances have a lot of variance. In other words, they have a lot of variability. And so we don't reject in terms of testing the equality of the variances. Okay? So that assumption seems to be okay. But the question that everyone is always interested in is, are the slopes the same? Now, thinking about the slopes being the same is thinking about, is there an interaction between the numeric variable, which is employees in this case, and the factor? In other words, do we have an interaction? And that's what we're really testing. So we had that nested model before, but the nested model gives us the parameter estimates. And in particular, I do that. Yeah. So let's, I actually did the models up here, but I didn't use them. Now, what I want to do is, the book shows you how to compute the common slope. Now, the common slope was a minus 1.51 roughly. Now, where did that come from? Well, do you remember when we did this? If I go back and look at the first thing I did, this is the first sections I did. Do you remember when I plotted this plot down here? That's the slope of these, and it came from, well, it's right here, but they're the same for all 3 groups. And where did I get it? I got it right here from this model. So that's the common slope. That is the common slope. Now the book, the book shows you, let me go back and re-execute this. So in the book, they showed you how to get the common slope. If you wanted to do it, where is this? If you wanted to use it computationally, you can go in the book, and this SP is the error. It's a sum of squares of cross products for the error term, and then this is the sum of squares for the error term for the x's. You can show that that gives you the minus 1.5. To compute that number is actually tedious, to say the least. That's why I'm not putting a lot of emphasis on a hand calculation. But I do want to show you how you can reproduce the numbers that are in the book. And then you'll think, boy, I'm lucky because I just run OR and I get these numbers and I don't have to actually do all these hand calculations. And as I said, maybe it's worthwhile looking through the hand calculations, but again, this is a very specialized case where you only have one covariate. You have a simple one-way analysis of variance. You have a single factor. It's a simple case, and if you generalize it at all, you're not going to be doing it by hand anyway. It's hard here. It can become effectively, you're never going to want to do it for a more complex model. Now, the book also defines these various quantities G and H, and they have to do with the sum of squared deviations. The sum of squares of deviations about the common regression line over all groups is called G. And the sum of squares about the individual regression lines, in other words, the residuals, for the unequal beta model, the more complex model, is called H. Now, you would expect, which one would you expect to be bigger? G or H? G is the sum of squares of the residuals about the common regression model, of all 15 observations about their respective lines. H is the sum of squares of the data about the regression lines, where I'm assuming they have different slopes. Which do you think will fit better? What now? H, yeah. The unequal beta will fit better because you're forcing the slope to be the same for all three. Now, in our case, there's not much difference because the betas are almost the same. So there's not too much difference between the model. But if the betas would be very different, then the H could be quite a bit smaller than G. So the way we test the hypothesis is look at the difference between H and D divided by the difference in the dimensions of the space, which is 2. Why? Because there are three. If you look at that design matrix, the X, the model matrix, there's a single column for the common. You have the employee column. You have that single column. Now, for those of you who know linear algebra, what these vectors do, each of the columns of that design matrix is really a vector, in an n-dimensional space. And we're looking at projections of y into that space, into different components. And so in the one case, we have a projection into a single degree of freedom. We're projecting into the space that has just the employees in it in a single vector. Whereas the other, it's a three-dimensional space because you're projecting down to 3 vectors. And the 3 vectors I'm referring to is this, and this. So I'm actually, when I project down to the space that's this, I'm adjusting for the fact that I'm looking at the space here that's orthogonal to the space here. This is what we mean by adjusting. In a geometric sense, we have a space due to media, we have a space due to employees. In this case, it's a 3-dimensional space. And I actually project the employee space onto the media space and get the orthogonal part, and then I project down onto it. And that difference is what we're looking at. Versus just projecting into a one-dimensional space. I have a one-dimensional space if I have all the employees with a common slope. I don't know to what extent I should get into this geometric interpretation. From my own way of thinking, it gives insight. On the other hand, you have to know a little bit about vector algebra and vector spaces. But underlying the linear model is, guess what? Linear algebra. It's just like, when people study databases and they say relational databases. And so, Oracle and all these big companies that make billions of dollars selling relational databases. Guess what underlies relational databases? Relational algebra. So if you know relational algebra as a mathematic topic, then the theory of databases is trivial. Just like if you know linear algebra, as a mathematical theory, then the linear models is trivial. But, this is an intro course, so I don't want to get carried away with linear algebra in this course. But that is what lies, there are various ways I can represent it not using algebra. This is one way that I'm doing, but there are other ways, which I probably will do at some point. I may stick some of this in a not too distant future. But if I look at, so the way I would test whether or not I have common slopes is I say, well, how much did I reduce the sum of squares? How much did I reduce the sum of squares by fitting 3 regression lines rather than 1? So that's G minus H. G minus H. And the difference is A minus 1, which in this case A is 3, so it's 2. In other words, I would have a I would have an A-dimensional space if I fit a different regression line for each of the A groups. I would have a one-dimensional space if I fit a single line for all groups. The difference is A minus 1. So I normalize, well, let's say I standardize, that difference G minus H, which is the difference in residual sums of squares, by dividing by A minus 1. So I'm sort of getting an average sum of squares per dimension of the differences in the fit. And then I standardize, then I look at the denominator, which is simply the more complex model, that is in our case, the 3 regression model. And that gives me an f-test that I can test equality of slopes. So that's all nice, except where do I get this in the R output? Ultimately, it boils down to, okay, great, but where is this information? Well, it turns out it's the interaction term. The interaction term between employees and median in our case. And in general, it's the interaction term. So let's come back to that in a minute. This is my model matrix. And in R, you can get this. One of the things I like about R is that you can actually get this because it gives you a little... And you wouldn't want to do this if you had a lot of observations. But when you have n equals 15 observations, it's not too bad to look at. But if you had 1,000 observations, you wouldn't want to print. You might print the first few. But by having a small data set here, we can actually sort of see the structure of this matrix. Now, a matrix has, n rows, and, we could say, okay, each row represents an observation, and each column represents a variable. In these cases, these are variables, but the median, those are called dummy variables because they're basically zeros and ones, or minus ones because of the constraint. And then the others are not dummy variables; they're actually real data, but they're broken out by group. So I'm going to fit a model. If I fit this same model, this design matrix will be the same as if I fit an interaction one. So if I fit this model, this is nice because it gives me the regression coefficients, just like we had before, using the summary statement. So if I cite summary of media fit 2, I must have done it again and actually called it media. Yeah, I did it again and called it, here I called it media fit 2. So at any rate, this is the model. Now, remember, we had, how many columns do we have here? 6, right? How many parameter estimates do we have? 6. You got one parameter estimate for each column. Now, if I think about this, and I haven't really covered matrix algebra at all, but if you take that matrix and multiply it by the vector of the parameter estimates, I get the predicted values. So if I would take that matrix, and this is matrix multiplication, and when we get to regression, I will talk about. I'm going to give you a handout. That's my 20-minute. Well, it will take you longer than 20 minutes to read it, but sort of my 20-minute summary of matrix algebra. Now, the nice thing about R is, I'm not assuming you know matrix algebra in this course, but in R, you can do matrix multiplication, scalar multiplications, inverses, all the things you can do in matrix algebra. In R, you can do. So I could take the model matrix and multiply it by the parameter estimates and get the predicted values, and I would be matrix multiplying. And so it's very easy to do this in R, and it's very easy to see what's going on. So you could take a few little sample matrices and say, okay, I have a matrix A, I have a matrix B, how do I multiply them together using matrix algebra? Well, you could just create a little matrix A, a little matrix B, and multiply them together. You better make the number of columns of A equal to the number of rows of B, however. But again, I'm going to give you a little handout on matrix algebra that I wrote for my multivariate course. Because you do need, even with the analysis of variance and covariance, knowing matrix algebra really helps to understand what's behind what we're doing. So these are the parameter estimates. The intercept is 56.49. median 1, this is alpha hat 1, alpha hat 2. And then these are actually the regression coefficients. Now notice, the regression coefficient was what? Minus 1.51, right? So now look at the 3. It's minus 1.46, minus 1.48, and minus 1.60. They're not far off. They're reasonably close to minus. They're not very, if I plot it, I'll have to stretch my eyes a bit to see what the differences are. And we are going to plot it. And you'll see that they look fairly parallel. But they're not the same. So we are going to plot the employees by profit just as we did before. And I'm going to plot a vertical line at the mean employees because again I'm going to adjust to the mean. But now I'm going to plot 3 lines. So the first line for the first group is 56.49 minus, so I take this minus this first group minus the 14.824. So this plus this, which is minus, gives you the intercept for the first group. And then here's the slope for the first group, minus 1.46. Now these are the 3 slopes. They are different. In the preceding time I did that, they were all the same, right? So here they're different. So how do I get the second intercept? Well, again, I take the 56.49 and I have a minus 6.14, which is this second one. And then the third one is that same estimate for mu hat, and then I do a minus alpha 1 minus alpha 2, which actually gets a plus sign. So that has the biggest intercept. So this is median 1, 2, and 3. I think that's the order. Okay, so and then I create this data frame, and this is I'm going to actually get a predicted value for the least squares means all at 31, and I'm going to plot these least squares means in blue, and then I'm going to get the sample means and plot them red. So that's exactly what I did before. The only real difference here is that I have 3 slopes. I don't have a common slope. And here's my plot. So it looks about the same, but can you see, and in particular, that top group has a steeper, it's a minus 1.61. Notice it drops down. Can you see that it drops down a little more quickly? The other 2 are almost the same. But, this is not one of these dramatic differences. Now, testing interaction is really testing are those lines parallel. And they're not far off. So you'd be surprised if we conclude that we need different slopes. So I used this model right here. I used this model to actually get the parameter estimates. And that allowed us to do the plot with all the nice little graphs and things. But I could also fit this model, median plus employees plus median colon employees. Now that's actually equivalent to the, if you look at the model matrix of that one, it's actually identical to the other one. But it breaks it out a little bit differently. So if I do the capital A ANOVA, it in fact breaks it out to median employees, median by employees, and residuals. Now, what I'm going to tell you is this 51 right here is H. And this 2, it's really 2.5. That's G minus H with A minus 1 degrees of freedom, which has 2 degrees of freedom. So G minus H divided by 2 over the H divided by 9. By the way, if you look at this, here's the A minus 1 is 2. The H has capital N 15 minus 2A, which is 2 times 3, or 9 degrees of freedom, and that's this. So this test with an F value of 0.22 is the F test, that's that F test I talked above, G minus H over A minus 1 times H over N minus 2A. That's that F test. And what do we conclude? Is 0.22 a big value? Not at all. It's not even 1. So the p-value is actually 0.81. It's not even close to being less than 0.05. This tells us we do not have an interaction. So the one model that I wrote let us get the individual estimates. This model up here, this model let us get these individual estimates, which let me do the plot and put the slopes and the intercepts and all that. This model lets me test the interaction directly, and these are the correspondences. Let's see, time-wise. Okay, it's time to quit. This is the corresponding, this is the corresponding what's in the book with the G minus H, and here we have the test, which is not at all significant. The final thing to do here, well, there's a couple of things. So I'm not quite finished. I'm going to have to sort of spill over. The next thing we're going to do, if we say, okay, I don't need that third term in the model. I can just have employee plus median. I don't need the interaction. Okay, so I can use a common slope model. Now, the next thing we may ask ourselves, okay, I can use a common slope model, but what if the beta is 0 and I don't need to covariate at all? And therefore, my model reduces to just a one-way analysis of variance on median. I don't need to covariate. So that's the next thing I'm going to test. And so, that we go back to this same model, and we're simply testing, if you have the ANCOVA, you're simply testing the employee effect. But in this case, we absolutely need it. But I'll come back to this a little bit more next time. This is where we'll start. And then the other topic we have to cover yet, the last topic here is multiple comparisons. In other words, how do we put confidence intervals on the adjusted means? That's the next thing I want to look at. And then we want to talk about differences of adjusted means and how do we do multiple comparisons on differences. Just like you did multiple comparisons on the one-way analysis of variance. Here we do it, but we have to do it. We always do it on the model means, not the sample means, but the model means. Here the model means are adjusted for the covariate. Okay, does that make sense? So that's what we'll finish up next time. So we'll finish up this particular chapter, and I'll probably then get started on chapter 14, which is the last chapter in the book. We're probably going to pretty much get through the book, which I wasn't sure of at the beginning. But I have, 2.5 weeks.